Okay, hello materials class. So PowerPoint handout, just like the one you're about to see, is on Canvas. It's been up since before that last homework quiz, actually. So it is up there under the files, and we're going to go with this document reader video. That seems to be the preference, and I think it's also going to enabled me to still kind of do a little bit of show and tell today. So obviously we're going to be talking about material failure, specifically about impact failures. We'll have also fatigue and creep failures, so two other types. So we'll cover three specific types of failure above and beyond just a tensile failure. So here we go. We're going to go through our slides. We have got a quick review of ductile versus brittle behavior. Ductile materials, significant plastic strain. So remember, this is going to be more or less where we quit being linear, right? So up here, approximately where we quit being linear, that should be elastic, and then the remainder of the material, deformation, will be plastic. That's the part that does not spring back. Brittle materials will have little or no plastic deformation. So little and no flex and bending. So we talked about before the area under the stress strain curve. If it is an area and you think about it as like height and width, like you would for a rectangle here, right? So we do an integral on this, whatever this fancy equation or shape is. Well, it's going to have the units of your y values times your x values. Just like if we were doing, say, a yard outside somebody's house, and we're doing it in feet, and it's, 100 feet and, I don't know, 50 feet, right? And it's, what's the square footage? We're multiplying 50 by 100, and it comes out in square feet. So just like we've got the units that multiply with the values, same thing here. Strain is in inches per inch. Stress is in pounds per square inch. So what's the area have units of? What's pounds per square inch times an inch over an inch? A pound inch is a measure of energy, because a pound foot is often what we measure energy in for moments, dynamics problems, that type of stuff. Inch cubed. So what is that? That's energy per unit volume. In this case, inches is our units. So energy per unit volume is your area under the curve. That is the energy it takes to perform this tensile test and deform and break this sample specifically. So we're still keeping with this concept that it takes energy to cause deformation and failure. Okay. So let's see, where does that leave us? Yeah, so back here we defined this as tensile toughness. Toughness is one of our most important material properties, and that is what impact testing is designed to measure. So we will, let's see, look at the next slide. I've got an oil tanker that has failed. You can find plenty of examples, in particular, of ships that failed under very brittle conditions. And so this failure across here is particularly brittle. We expect it to be ductile. And that's where impact failures can be particularly dangerous, is that we expect ductile behavior and get brittle behavior, which requires what in energy, more or less energy to break it, less, right? Less energy. Okay. I always imagine, what are these two guys sitting here doing? So fill in with your own text box what those two guys are talking about right there. So anyway, the shipping industry, particularly the U.S. Navy, is where the study of impact started. So World War II era, some naval officer said, wait, why are more ships sinking in the Atlantic than the Pacific? Same type of ship getting hit by similar torpedoes, similar conditions. Looking at the failures of the ships, they looked more brittle, acted in a more brittle way, and so they determined, really by trial and error and some good old-fashioned experimentation, that the temperature of the water did in fact influence the failure behavior of the ships, and started to study that. So the way in which we modern study this is with impact testing. I will find a YouTube video of this and post it later. This is specifically with a Sharpie test that we're showing. There's a couple of other tests, but this is the most common. It is a 100-pound hammer specifically designed with a curved indenter on the end of the hammer. So here's our hammer. It has a curved, not indenter, impactor, excuse me. I guess it's going to leave an indent probably. Anyway, it strikes a sample that is 10 millimeters by 10 millimeters by 55 millimeters with a specifically designed notch in it. And so this is called a notched Sharpie, named after some guy, impact test. We will use this to determine a materials, so materials possessive behavior to impacts slash high strain rate. So really the same thing. An impact loading produces a high strain rate, so it's going to try to deform the material very quickly. Also testing the material behavior to temperature changes. specifically concerned with failure of the material here. So materials failure behavior. There we go. The way in which the test is conducted is we have a starting position for a 100-pound hammer in an elevated position. It is allowed to free fall through an arc, strikes our sample, breaks our sample, and what we're really measuring is this height afterwards. So there is a height H, which is our starting height, and then they've got this labeled here as H prime, which is our height right there. Okay, so the after height. So after our specimen is broken, what is the maximum height of the swing that it goes up on the other side of the specimen? That's what we're measuring. So we will measure off of a scale here that tells us the energy absorption of the specimen, usually a metal specimen here, although you can do other materials. There's some data in the book if you happen to have it on like nylon, some other plastics, but most of the time we're looking at metals. Okay, so what are we really measuring to get an energy value? So we start at a specific height, we end on a specific height, that's all we're measuring. We know we've got 100 pounds force, assuming standard temperature, pressure, acceleration of gravity, all that can convert into a mass. So we've got a height, we've got a mass, and we're worried about energy. Well, what type of energy do we have? Everybody's had dynamics. Potential energy, right? So mgh, mass times gravity acceleration times your height off of, you know, your ground level or whatever. In this case, it would be the bottom of the swing would be h equals 0. So we come over here, we have a different height prime. So potential energy here. Our mass should not have changed. Gravity should be the same. What do we have? We have a height difference. Change of potential energy equals mass times gravity times h minus h prime, right? This is our delta H. Change in height before and after. That energy difference, where did the energy go? Sure, a little bit went into air resistance, a little bit went into the friction of the bearing up here. Your vast majority of your energy goes into breaking this specimen. So what are we really doing? We're checking the energy to break that specimen really by calculating the change in potential energy. What is this scale up here on the machine doing for us? It's giving us change in potential energy. That energy is our energy to deform and break our specimen. So, change the specimen's temperature, and we can see how does temperature changes affect the failure behavior of the material. So, you can pull these out of a furnace. I've seen people pull these out of a little bucket of liquid nitrogen sitting next to it. You just have tongs. You don't stick your hand in there. But they have tongs that grab these samples and actually center them in the machine very rapidly. So it's a by hand thing where you grab tongs and can move it over the machine and center it without having to check it. The tongs themselves do it for you. So anyway, This is our modernized version of impact testing that we collect data from. One of let's see, so there's a couple of different things that we look at from this. One of those is ductile versus brittle behavior. So this is a picture of a broken specimen. So this is half of a broke specimen. In this case, we've got a couple of different regions. We've got this region and then the region out here. This is the notch. So that's actually sloped. That's where the notch was cut into the sample. Ignore it, right? That's not part of our actual failed material. We're looking at this region, this innermost region, which is going to be brittle. It tends to be flat, and it tends to sparkle. I'm going to show you one of these using the document camera in a minute. The other area is ductile. The ductile region, under normal circumstances, surrounds the brittle region. If there's a ductile and a brittle region, there doesn't always have to be. The ductile region will be dull, usually a dull gray. A lot of materials will fail with sort of a gray surface. Doesn't have to be, but it won't sparkle. Shouldn't sparkle. So that's what I'm talking about when I say it's dull, and it's usually at an angle, and that's because there is shear. So shear failure tends to happen at an angle. Okay, so impact failures, we can find both ductile and brittle behavior on the same specimen. When we're dealing with tensile, say like a tensile failure, so slow loading, not impact, we're usually looking at ductile or brittle. Traditionally not both. In this case, we can get a mixed. We can still be all ductile or all brittle, but we can also get a mixture of behaviors. And we're going to try and take a look at that here on our document camera. Okay. So let's see. We're going to hold this up. We're going to refocus. It almost did it. Not quite. Okay. We're going to zoom in. Here we go. So this was some 304 stainless steel hit at room temperature. This is the impact from the hammer. The specimen did not completely break. It tore some at the notch, but there's a pre-existing notch in this specimen. And where did... Oh, just a second. Untested sample. So we have our pre-existing notch. and nothing too fancy. This one was like this, so there's some of what looks like failure up here was the notch already existing. So this is a very tough material. It's a more expensive stainless steel. It's meant to be tough. It's meant to be tough at cold temperatures. So we'll talk more about that in a little bit. But this is an example of an austenitic stainless steel. Don't worry, I'll write that down later. Here's another ductile material. Let's see, let's play fit the pieces together. There we go. Our notch was up here. So the specimen was like this, impacted from the back, bent forward, snapped apart. These are ductile failure surfaces. They happen at a slight angle here. Okay, they are not particularly sparkly, not when compared to, say, cast iron. This is a non-standard sized cast iron sample. It's larger, it doesn't have a notch, but you can see there are sparkles on the surface, and that is characteristic of a very brittle failure. And relative to this, we see sloping along here on the failure. Here, this is very flat. It occurs very parallel with the direction of impact. So this one was a 4140. There we go. So that's a chrome moly chromium molybdenum alloy steel, medium carbon. It's very weldable, pretty common on, say, the Baja car, automotive parts, stuff like that. Of course, this is cast iron, used for machine bases, engine blocks, brake discs, of course, cookware, but that's not a big part of the industry. But it is characteristically very brittle and has terrible impact toughness. We also have an aluminum sample. Let's see if that focuses. There we go. That's a little too reflective, but shows some deformation. Take the pieces apart. There's our notch up here that we're ignoring. And this is very ductile for the most part. And the middle of it is kind of brittle, but the outside, there's an outside layer around it that's very ductile. I know that was 6061 aluminum, but I don't have the temperature. It looks like there's a room temperature. Okay, so I've got a whole box of these, but I think that gets the point across, and I think we can reset our zoom. Put the next page down, make sure we reset our focus. When we are doing this test, we tend to get data that looks like this. Well, I'm going to skip to the next slide. Talk about this for a second. So this is an expanded view of this. As a matter of fact, we're doing this slide first. So here we go. Impact energy. So this is going to be in something like foot-pounds or joules. You could do it in BTUs or calories or something, but it's pretty much foot-pounds or joules because it's going to be potential and kinetic energy. So temperature. Careful with our temperature scale. Right? This is hot, warm. This is cold. Okay? So sometimes people have a tendency to kind of reverse the direction of that. Usually in materials, we tend to want high impact energy. Why? Because they don't break when people drop them. They don't break when somebody bumps into them. They don't break in an automotive collision, etc., etc. Um, so, or if we're talking about, say, just something as simple as gears, right? I'm going to do some not to accuracy gears. The reason we don't want, say, a really high carbon content throughout the entire gear, right, goes back to carburizing. We want a hard surface, but we want a soft inside. We're doing that for toughness because your really high carbon area is going to be something like this. Your low carbon area is going to be more like this or at least this. So as long as our gear is warm, it's got a high impact energy, high toughness. Starting and stopping these gears suddenly, let's say we suddenly apply a torque on this gear and this gear is passive, it's receiving the torque. These teeth are impacting against each other. If this material doesn't have a high enough impact toughness, the teeth just shatter off in a brittle fashion. Just one example, any stop and start sequence in a motor of any kind, a pump of any kind, planes, trains, and automobiles, all of that stuff, you're going to want impact toughness. So sometimes people will say impact energy. Sometimes they'll say toughness. Sometimes they'll say impact strength. Technically, this is not a strength, okay? Just so you know, impact strength is a bit of a misnomer. It is common for people to say it. You'll find it in textbooks. You'll find it on the internet, okay? But just technically, this isn't a strength. It's an energy or a toughness. But all three of those, people are talking about the same thing for impact. So impact energy, impact toughness, impact strength. All should be a measure of the energy it takes to break a specimen. So, really high strength materials, that actually goes back to a lot of our ceramics, including even window glass down here, guys. That's the example we started with when I talked about why don't we make a classroom building out of glass. Here it is. This is why on one slide, because this is glass. This is steel that is really, really hard, like something we make a knife or a sword out of. Up here, this is more like copper alloys. This is titanium. This is a lot of your aluminum alloys. They are tough, oftentimes face-centered cubic, sometimes HCP, okay? If you look up like zinc, zinc is more down here than it is up here. So this includes titanium, but doesn't necessarily include all HCP materials. In general, they tend to resist cold temperatures and retain ductility. So it's especially FCC materials. Your high strength materials, these tend to always be brittle. Okay, well that's well and all good, but where we discovered with our ship sinking, going back to that example, this behavior, we get a transition from high impact energy down to low impact energy, usually at the halfway point. We'll label it as a DBTT, which is a ductile to brittle. I'm going to run out of room. transition temperature. So ductile to brittle transition temperature. Why at halfway? Because that's fairly straightforward to measure. If we went up here and said, well, as soon as you start losing energy, that's nebulous and difficult to measure if you look at real data. So the halfway point, when you've lost half of what you think your highest energy is fairly straightforward to measure and report. Really, this is just a way to compare one material to another. So if this is one steel, right? Steel is usually body-centered cubic, versus here's another steel. Here's another steel. Which one do I want to use at cold temperatures? What do you think? Well, if I know I'm going to be cold, I am brittle in this situation over here, this situation over here. This one gives me the highest toughness at some of the coldest temperatures. So I've still got half my toughness when this curve is almost flatlined on its toughness, and this one over here it'll eventually flatline and reach a minimum toughness, which is going to be like throwing a glass cup against the wall or something. Right? So if we're down here, we're going to behave like somebody taking a hammer and hitting a glass window. Okay? So one of the examples we'll come back to is the Titanic. That's what happened to the Titanic. How do we know it was cold? Maybe because there was an iceberg in the water. So yeah, it was probably cold. That was in the Atlantic. Again, the Atlantic Ocean is colder than the Pacific Ocean. The Pacific Ocean is a tropical ocean. The Atlantic Ocean, especially in the right season, tends to be, have icebergs floating around in it. So this graph tells us, how does our toughness or energy absorption relate to temperature? It's one of the reasons that we do this test. So going back to the previous slide, that's what this graph is trying to talk about. So again, this is often called the high shelf because it looks like a shelf sticking out on the graph. So guess what? This one's usually called the low shelf. Okay, so when we're at 50% in between the two, or 50% down from our high shelf, that'll be what we call the ductile brittle transition temperature. It's what we're reporting here, and it's just a way to compare materials and say which material is better in a cold application. What we're really doing is looking at, here's stress, strain, and temperature in 3 dimensions. So this is meant to be 3 dimensions of information. Well, at high temperatures, we're very ductile. So this would be a high temperature. Very ductile, lots of energy under the curve. As we move towards a very cold temperature, our stress strain graph looks very brittle. We get little or no plastic deformation, and we have very little area under the curve. Our material can be really strong. This is meant to show that at a cold temperature, our ultimate tensile strength is actually higher. It goes down as we get warm. Okay, so compared to our stress axis, a very cold material is actually often strong in terms of ultimate tensile strength, but the area under its stress strain curve is very small. That relates to your impact toughness. So here's glass, right? Here's a lot of ceramic materials. Here's a really, really hard steel, right? So it's got its applications, but it's very brittle and it has very low toughness. Over here, this is getting more into the range, maybe something in the middle ground here. This is what we want to build a lot of automotive components out of. Why? Because it's reasonably strong, which means I can make my components smaller and save weight, save fuel efficiency. But in an impact, like an automotive collision, there's still reasonable energy under the stress strain curve. This one is just very brittle versus very ductile. It's not the greatest picture. I think my video gives you a better example, okay? So, set that aside. Here's for an ASTM A283 steel. I think that is like a bolt steel for structures. Don't hold me to that, but that is a standardized steel. Here's impact energy in joules. We have some real numbers. Celsius, Fahrenheit. As we get colder, we get more brittle. We can also graph on a second y-axis percent of shear fracture. This is ductile. Percent ductile fracture area. So if I back upwards to this slide, we're looking at probably just knee-jerk reaction about 60% ductile. That's the area outside here. Area inside, probably about 40%. Exclude the notch, right? So that would be 60% shear fracture because ductile failure will be shear. Well, so where would we be? We'd be right about here. And then, so at that given temperature, we would have 60% shear fracture, and then our impact energy would be up here. So we would say, pick a temperature and look up and down our graph and say, well, what's our impact energy and what's our percent shear failure? That was by looking at the failure. Or we could pick a temperature like, well, at 70 degrees, how ductile am I? 70%. How much energy do I have? 90 joules, right? So approximately. So we can relate our amount of ductile failure area and the impact energy. So, and that's for a real steel. Notice that a lot of our steels, this one's no exception, they're very brittle over here around the freezing point of water. Actually, I start at 0 Fahrenheit here. I'd start at 0 Celsius, right? 32 Fahrenheit. So, okay. Austenitic stainless steel. Maybe you've seen this thing sitting out in the hallway of EPS out on the west side. This stores, guess what? Liquid nitrogen. That's why it says nitrogen on the side. This is going to be made out of something like alloy 304 stainless steel. That is a 3-digit numbering system for some of these high alloy stainless steels. Here is why we care about that. Let's see. That was room temperature. Well, let me just go back to this. This doesn't change much once we put this in liquid nitrogen. It does become a little more brittle, but it still retains a ductile failure surface. What does that mean? That means by making this out of a high alloy stainless steel, like this material, if I accidentally bump a wrench into this, it doesn't shatter down the side and release liquid nitrogen all over me. I would prefer that as opposed to being covered in liquid nitrogen. So, this material is what we're going to make that out of. Very, very tough, very, very ductile, but also with fairly reasonable high tensile strength. So we call these austenitic because this is a root word that in steel means gamma iron or or face-centered cubic. We're going to try and fit in steel metallurgy and heat treating by the end of class this semester. We'll see if we get there. And we'll learn that there are special names for our different conditions in steel. So face-centered cubic gets named austenite. Body-centered cubic gets named ferrite. There's a variation on body-centered cubic that's body-centered tetragonal. It gets named martensite. What are these named after? Well, they're usually named after something like Sir William Frederick Austin III, right? So some name like that gets this named after them. Steel is the only metal that we do that with. It is so critically important to the Industrial Revolution and the industrialized society that its crystal structures and different microstructure features all get its own special name. But this is a category of steel. You can go online, look this up, find some to buy. So most of our steels have a ductile to brittle transition. For our austenitic ones, temperature and energy, guess what? Face-centered cubic steel, tough, even way down here with liquid nitrogen. Yay, that's what we want. We didn't have those when we built the Titanic, by the way. These are a modern invention. At least we didn't know that these were good for this. We'd never build a ship out of this anyway. So, but this is an application of this. I've mentioned these at some point earlier in class in the semester. So we really don't see a ductile to brittle transition here. This really lacks a ductile to brittle transition. Of any significance. So finally, I've got an example based on some slides that I borrowed from someone. So I went to a conference and saw this. So here we go. Real interesting person. She presented in blue jeans, a t-shirt, but put a sport coat and a tie over it. Anyway, so here we go. Dr. Irvin. Back years ago anyway, it was at the University of Mississippi, and they looked at a failure of a bridge. This is the I-35 bridge. I think this is on the southern side of Michigan. So we do actually see cars here. I forget how many people died in this collapse. There's a little bit of glare on this picture here. But what is going on in these pictures? This is the collapsed bridge. Here in this picture, if you're able to get a good look at it, there are sensors taped to a few places here with some cables. Okay? They knew that the bridge was failing. So they strapped on strain gauges to monitor vibration and monitor the flexure of the different steel beams. If you're a civil, or if you listen to some of them talk about civil things, you'll know that they over-design everything for good reason, because we don't always detect a failure early enough. We don't always know what all the operating conditions are. And so we'll take a design and we'll slap on a safety factor. Like, oh, hey, I need an I-beam that's this long. Well, let's just double it. Things like that. Or that thick or that height, not that long. So you're taking your cross-sectional area, you're doubling it. Something like that, okay, for your factor of safety. So, so they knew that there was a series of cracks. They were monitoring those, and they thought they knew how long they had to make a plan to take the bridge out of service and divert traffic around it, because it went over a major river, and this was a major economic interstate. Well, guess what? Their analysis was faulty, and it was faulty because they considered all of their loading to be static. Okay, so here's one of the failed plates that they were examining. So here is the way that they did their experiments. They modeled up bridge joints in a lab and looked at loosening some of the connections because the plates were simulated the plates failing some. So now we get a rattling and a shaking in loose joints. Modeling that is very complex. But basically, once we get a loose joint and we get motion back and forth, we now have impact. And so we've taken something that we consider to be static and have static loading, and now it's a dynamics problem. Beyond that, it's dynamics, it's material science. If I can not mix up my letters. So it's dynamics, it's material science, it's also machine vibrations. So what we thought was a civil problem is now a mechanical engineering and a material scientist problem. So this becomes very interdisciplinary. We've now got kinetic energy involved. So this is one of the dangers of impact failures. Not just that, hey, temperature shows up, not just that a normally ductile material may become brittle. Now we're also looking at situations where, well, what about things that we're analyzing as static? Now we're adding kinetic energy in addition to a normal stress. So anytime you take stress and you add kinetic energy, it becomes very problematic to analyze and often rapidly promotes materials failures. So kind of picked on some civils, but hey, let's pick on, say, Baja teams, right? So usually what happens, usually it's a situation where their car fails, an axle snaps, a bolt snaps. Suspension is a common failure because you take your little car up off of a ramp. Woo, there's our little Baja. There's somebody having fun. They come down on one wheel or just two wheels, maybe, sometimes one wheel. Your landing gear now has a bunch of kinetic energy going. Your landing gear. We'll call it that. We'll stick with landing gear. What is your suspension now becomes landing gear, and all your kinetic energy goes into one wheel and one set of rods, A-arms, that type of stuff. Yeah, oftentimes that's where we see the failure and we see the design being under-designed. It's very complex to go into even FEA software and model that. So there's that. Finally, quick blurb. Fracture toughness is a whole other area of study. So fracture toughness is not the same units. It's not the same thing as impact toughness. So bad naming system. Used to, I would get lab reports and it would be real easy to see if somebody just Googled a number, because this comes out in like 1 over square root of inches or something with weird units. This is supposed to come out in joules or foot pounds. So I go, what did we find for the impact toughness of our steel? And they give me some number like 2.3 1 over square root inches, and I'm like, yeah, you Googled that, you know. So we're not going to go over fracture toughness. It's a more advanced topic about analyzing brittle failures in particular. Real quick, I want to throw up actual data from the Titanic We're going to have to zoom in on this, refocus. So here is impact energy and temperature like we're looking at. This is modern structural A36 steel, common I-beam steel. These are samples cut out of the Titanic. So you had a plate, and I'll drop here, like a whole plate. During manufacture of this will be rolled through rollers. So it'll have a direction. We're talking about, do we cut out our Sharpie bars in this direction or in this direction? Not to scale. These would be very, very tiny compared to the overall structure. But it's about the direction. Are we parallel or perpendicular to the direction that this plate was rolled in? So you do get different properties, but you look at, even in best case scenario, the toughness of the Titanic steel compared to our steel, not very good. Freezing point of water, the Atlantic Ocean is not at the freezing point, but if you've got icebergs rolling around in it, you're not up here at room temperature either, right? So we are looking at Titanic steel that was probably down here in port. It was probably up here during manufacture. It's up here. We're past our ductile to brittle transition. Here's our percentage of shear fracture done on a separate graph. Your data for both sets of the samples, whether they were transverse or longitudinal. So that's talking about, is it in the direction or is it 90 degrees to the direction of rolling? There's your modern steel. It's just ductile all the way around. Compared to a tensile test, the steel's not bad. Compared to a lot of factors for steel, the Titanic steel was fine. They didn't make it wrong. They just didn't know how to make steel yet. Again, this is a post-World War II discovery, which in terms of metallurgy is super modern, right? Think, Bronze Age, Iron Age, the development of blacksmithing and everything. A lot of this stuff was discovered hundreds or thousands of years ago. So something like a discovery like impact toughness and the effect of temperature being within, the last several decades is very modern. And according to things like hardness, yield strength, ultimate tensile strength, the Titanic steel is fine. Where we've discovered that it was problematic is in things like this. In particular, this is a capital P and a capital S. I'm going to leave you guys to figure out what that is in the periodic table. No, I'm just kidding. We're looking at phosphorus and we're looking at sulfur, right? That's easy if you didn't remember. Titanic whole plate, phosphorus 0.045% by weight. Modern steel 0.012. For sulfur, 0.069% versus 0.037%. Also problematic, manganese is a little less than in the modern steel. Sulfur we can handle being larger if we increase the amount of manganese with it. So manganese is generally a good thing, especially if your sulfur is high. Here we have high sulfur, slightly lower manganese, very high phosphorus. This is a very high phosphorus amount. Phosphorus is pretty much universally bad for iron-based alloys. Even in such tiny amounts, they contribute in particular to low toughness and a high ductile to brittle transition. So what do I mean by high? At higher temperatures, right? This would be a lower ductile to brittle transition. So a high ductile brittle transition temperature is bad. And these contribute to that. So we increase our ductile to brittle transition temperature. So that goes on. Quick story, when I was in graduate school at the University of Missouri at Rolla, I had a shop tech call me in his office one time, and I was like, I didn't break it. I don't know what it is, or what you want this time, but, and he goes, no, I just want to show you something. He pulls a rusty block of metal out of his desk drawer, hands it to me, and goes, that's a piece of the Titanic. I immediately go, BS. I'm not going to believe you, blah, blah, blah. I'm handed it back to him. And he's like, no, man. Like, he gets a little upset with me, and I'm like, yeah, whatever. I go to teach this class for the first time, and I go and look this up. These figures come off an article you can find online called, in the Journal of Metals and Materials, JOM. There's a magazine version of the article that talks about the work to produce these results being done at the University of Missouri at Rolla. And in the thank you section of that article, that guy's name is in there for machining and preparing Sharpie samples of the Titanic hull plate. So I don't know, did the guy steal a piece, or is he just telling people that a random rusty block of metal was a piece he stole from the project? I don't know. Maybe I've handled a piece of the Titanic, maybe not. There's a pretty good chance he's still pulling people's legs, but it's possible. Okay, anyway, homework. I'll post some stuff on Canvas. We'll try to come up with something to do for a homework quiz middle to late next week. I don't know what that looks like yet. I don't think that I can do something like, hey, fill in the blank. It is a blank toughness. I mean, because it's going to be open note. So I don't think that tests knowledge or learning. I will let you guys know. I am working on grading the diffusion problems. There were about, I think, 9 different variations of that question, and the one that you got pulled off of Canvas was random. And in addition to that, 5 or 6 people did something that created a different diffusion coefficient or something else along the way in their problem. So I've got 14 or 15 unique questions to grade, which means I have to sit there with the calculator and work that problem through uniquely every time. So it's just going to take a while. We will get through this. We'll do some more of this. If you have questions, please email me. If you need to set up a Zoom meeting with me, I've been doing those for advising anyway, so I'm doing video chats. I can even try and work a problem at the marker board or something if I know in advance enough. So we'll try and help out when I can. Get emails all day long on my phone. I'm trying to respond to them, trying to do advising and everything else. I hope everyone's okay. Stay safe. I'll let you know a time window to take a homework quiz. I'll still do something like try and give you a few hour time window because I know everybody's schedules can be mixed up. Your internet access can be sporadic. I'm going to try and upload this both on YouTube and Canvas if I can get that done, just to give people the most options to get to it, maybe different options for buffering and resolutions to help you out. Trying to think. That's all I can think of. By the way, some of the temperature ranges actually produced a slower carburizing time. So if you're one of the people that was freaking out that the time took slower, there is actually a couple of temperature ranges in there where that happens. And so you can quit losing sleep over that if you are. I am working on an Excel spreadsheet and some explanation that I'll post a video of why that happens. So you guys will probably learn more about that than you want to. Okay. So anyway, that being said, as I started to grade those, I discovered that, and then I had to go come up with an explanation for it. So I'm going to stop the video and try and get this posted.